Okay, so now we have a force versus time graph. And so the first step when we're always analyzing graphs is to think about what are the axes. The area under the graph is going to be f times the change in the x-axis. The slope would be the division, force divided by the change in the time, and then the y value just equals the force. Okay, those are the three things you kind of want to consider when you have a graph. Now, force divided by time is not something we talk about, so that has no meaning. But the area does have a meaning. This is the change in momentum. Now, I cannot just take an f and multiply it because the f varies over time. So that's why we have to do the area under the graph instead of just multiplying f times delta t. Because if I ask you, well, what is f we're going to use? Well, it depends. It varies, right? The force is going to vary over the time. So there's no constant single f value I can plug in. So instead, the way we do it is we find the area. Okay, so the area is going to be the impulse which caused a change in momentum. Now, let's take a look at what the question is actually stating now. The force versus time graph for a child's toy car is a mass of 0.756 kilograms. The toy is malfunctioning and producing a force show. What is the velocity of the car after 20 seconds if it starts from rest? Okay, so let's think about this equation again. This is really the key part of what we're going to be doing when it comes to momentum analysis, okay? So instead of now calculating this, we're going to calculate this part, the f delta t, by doing the area. Now, the area what that means is it's the area under the graph from 0 to 20 seconds, right? So that's the area here. So we're just going to split it up into maybe a triangle and rectangles. Like, let's say we just split it up. There's this rectangle. This rectangle area is 5 times, what is this? 6, 7, 8. This is 8. 5 times 8, which is 40. This part here is made up of, like, this part is a rectangle. And then we have these two triangles here. So this triangle is half of 1/2 base times height. 1/2, the base is 5 seconds. And the height is from... Oh, I'm sorry. I'm sketching it wrong. I've already sketched the area wrong. The y value is 0 here. You're always sketching the graph to the 0 axis. My bad here. So we're doing this area. I misread the axis there. And then this area. This is the area we want. Okay, so let's do... This is still 8. Because each of these is 2. 2, 4, 6... No, so this is 6. So then the area, so we'll make this a triangle. This rectangle has an area, the width is 5, the height is 6, so that's 30. This is a triangle, the base is 5, 1/2 base, and the height is 6, which is 15. And then this area is below the 0 axis, so it's a negative area. So it's negative 1/2 times, what's that width there is 5. And then this height is 10. Or you can think of it as 1/2 times 5 times negative 10. Anyway, the area, the amount needs to be negative. So that's negative 25. And then there's no area here because it's right at the horizontal axis. So then the impulse is going to be summing up those areas. 30 plus 15 minus 25. And that's going to give you 20. Now let's work on the change in momentum, which is the m times the final velocity minus m times the initial velocity. Sometimes later on we'll talk about just calculate the final momentum, calculate the initial momentum separately. But this one's like, if it's a single object, it's pretty easy to calculate the final momentum. So the mass of the car is 0.756. And the final velocity is what we're trying to figure out. What was the initial velocity? Well, it started from rest. So it had an initial velocity of 0. So this just ends up 0.756 times v is the change in momentum. And then we're just going to set these equal to each other. The impulse is the change in momentum. So then v is 20 divided by 0.756. And I get 26.5 meters per second. What's the velocity of the toy car 20 seconds after if it starts from 10 meters per second? Okay, so now the impulse is still the same. 20, it's the same graph. However, the change in momentum is a little bit different. Because now it's 0.756 times the final velocity minus 0.756 times 10. Okay? All right? And that equals 20. That impulse has to equal that change in momentum. So then you can solve for v. So now you're going to take that 20 and add 0.756 times 10. And then you're going to divide by 0.756, and you're going to get 36.5 meters per second. Okay? And one way to think about it is both this was the change in the momentum was 20, and the change in the velocity ultimately was 26.5. So when I added 10 to the start, the end ended up the same. But this is the principle. You want to think about the impulse and the change in momentum as separate things that we're going to calculate.